Good evening, everyone. So this is tonight, and it really is sort of the last new type of derivative we're going to need to take. So we're sort of done with derivatives at least how to take particular functions of derivatives. There is this implicit differentiation we'll talk about on Tuesday, and what that is if we have two variables, so we have like x squared and y squared and a couple of, so we'll look at techniques for that, but it's the way we go about taking the derivative won't be anything different than what we've been doing, except we'll be doing it with two variables, okay? And the cool part is I think it's cool, is the related rates is really just an application of the implicit differentiation. So again, not a new way of doing the derivative, just having multiple variables. So we'll have those together. When we go over maximum and minimum, we're looking at applications at the same time. What do you think happens when we're at a maximum? What kind of a derivative are we going to have? Horizontal line, right? Tangent line would be horizontal. Zero, derivative zero. We have a minimum, same thing, going down, derivative is going to be zero. So that's all it is. We take the derivative, find where the derivative is zero, we'll find our maximum and minimums. We'll also be able to see them on the graph, so that's kind of nice. And then higher order derivatives is just, we're taking a derivative of a derivative. So eventually, most things, if you take the derivative enough times, it all disappears to zero. Not all of them, we'll see. But so tonight is the last really content type of derivatives, and we're going to just kind of get practice with other techniques and stuff as we go through. Elasticity is a business application. Elasticity of supply and demand or something. I know some of you guys know about this. I don't. It's a business thing, right? Elasticity of supply. And anyway, it involves a derivative. So it's an application problem. But it's suited, it's in the business. And then we'll get our review, we'll have our exam, and then we get to the second part of the course, which is going backwards. Okay, so it's kind of a big... In a sense, it gets easier because it's the same thing, but you have to be able to read it backward. If you can see things backwards. For me, it was easier because actually I see everything backwards. Like when I learned, I studied Russian because they have a backwards R. That's how I used to write my R's. I did everything backwards because I'm dyslexic. So in a sense, for some of us, it's easier. And it actually starts to make a little bit more sense. You go, oh, that's how I was doing this. And so that's the idea. Okay. But tonight, let's take a look. And tonight's derivatives are actually very simple, which in a sense makes them difficult, if that makes sense, right? They're so simple sometimes, especially one of them. We're going to look at two different types of derivatives, that it doesn't seem like we're doing anything, or that, so we're going to take a look at that. Let's see. So let's get into it. So I've just kind of put test one stuff down. Also, if you haven't gotten your test back, I do have them in my office. You're welcome to come get them during office hours, or just send me an email and I'll bring them to class next time if you haven't picked them up yet. But I still have a stack of them, and I think we got all the way. Through the makeup test tonight. So what I'm going to do is I'm going to post this. I'm going to publish it. And what is this? This is my, well, maybe I will publish. Oh, there we go. This is a scan of me working through it, so you'll see my solutions. It's not the only way to do it, but it, so especially on the open answer ones, you can take a look, and I'll just be honest, on the, some of those, it's kind of it's somewhat arbitrary how many points. So this should be, up when we get to partial credit. So if you want to talk about it, I'm open to talking, and make sure it's all fair. Because sometimes I might miss something. I look at it and I didn't see it that way, but you explain it. Oh, now I see what you were doing. That should have been 5 points instead of 2 or something, So it wasn't the right, still wasn't the right answer. Usually if you got the right answer, you got all the points, but anyway, let's take a look, make sure those are all going to be fair. But that's there for you to review, everyone to review. And what we'll take a look now is we're going to look at exponential and logarithms, how to take their derivative. So I just get into the slide deck. We'll turn the slideshow on. And what I'm going to do is I'm going to start with just an exploration. We're going to look at the graphs of a standard exponential, standard logarithm. And we're going to have Desmos give us the graph of the derivative to see if we can kind of guess what the derivative might be. If we can guess it, we'll graph it and we'll see, hey, that's how it is. This is sort of my way of doing a proof. I took out of the PowerPoint, they had like 2 or 3 pages of actual mathematical proofs that use limits that we didn't do, so they'd be hard to follow, right? And not really enlightening anyway. So we'll do it this way. If you want to see those sort of mathematical proofs all laid out, they're in the textbook, but again, I think they're not as helpful as what we're going to do right now. Okay, so what I'm going to do is I'm just going to put this function, call it f of x, and let's do a logarithm. Let's just do the natural log to start with. So that's the graph of the natural logarithm. Is that familiar? You've seen that probably in an algebra class, how to deal with them. Thing is usually when we have you deal with an algebra class, it's sort of at the end and we don't do it real deeply because there's not a lot of applications. There's the Richter scale for earthquakes. That's a logarithmic function. There are some things that are in there, but anyway, we don't do it a lot. So what's nice about Desmos is we can have it take the derivative. So I just type in d over dx, and that tells it take the derivative of whatever I tell you to take the derivative of. Did you know that? Now you do. F of x. And what it will do is it will actually draw the graph of the derivative. So the blue graph is the graph of the derivative of the natural log. Does anyone have an idea does that look familiar to anybody? Oh yeah, I just carry all these graphs in my mind and what kind of a graph that does that sort of that blue thing? So notice, just thinking of limits as x goes, what's that?
Limits to infinity.
Yeah, as x gets close to 0, it's going up to infinity. What usually causes that? What causes graphs to, as they get close to 0, to go to infinity? Limits, but what kind of a function? The limit of what kind of a function? Exponentials kind of have that look, but they don't necessarily. Rational functions, where we had the division by 0, remember? We get this sort of thing going on. So what kind of a function would have 0 in the denominator when x goes to 0? X is going to 0. 0 is in the denominator. What might have been there? It's a real simple function. 1 over, there you go, you got it, just guess, right? So let's give it a try. So let's see if I graph 1 over x, if it matches up. It's kind of like math magic here. Oh, 1 over x, I forgot what I was doing. And I'll just put it as y equals 1 over, drum roll please. Look what happened. The blue went away because it got covered by the green. So, and actually, this is a new thing right here. Why wasn't this here for the derivative? This part where x is negative. What do you know about logarithms and negative inputs? Asking too many questions about these things. Can you put a negative inside of a logarithm? You can't. It's undefined, right? So that's why when we take this off, notice there's the blue, there's that. We get 1 over x actually does have these two, but the derivative of natural log is really just 1 over x, but since since natural log doesn't have any negative x's in its domain is just 0 and greater, really it's just this part of it. So we're going to take a look of it. Basically, I can take the derivative out of there, and I can take this one out, right? There's the blue, there's that. They looking identical, and they actually are, except for that negative part, okay, because that's not in the, so we'll just kind of keep that in mind because we're going to talk about it. So what could we say is most likely the derivative of the natural log of x from looking at these graphs? 1 over x. Makes sense, right? So we'll go through, and that's what it is. That's what we're going to say. Could have took 2 pages and done a bit of math to prove it, but now we see it, right? Seeing is believing, I think. Well, what if it wasn't natural log? Because there's other kinds of logs, right? Let's see if I can do this. I think, can I do like log base 3? Let's see, how do I do? I think I have to go to functions, and then I think they give us here, yeah, log base 8, there we go. So I'll get log base, let's go with 10. Oops, not there. Let's get rid of this stuff. Let's do log base 10. Oops. Thank you. I would have been fighting with it all night long. And then we'll get one of those parentheses out of there. So now, notice, let's get this out. Let's turn this on. So this is log base 10, which is a common logarithm, and this is the derivative. So let's see if that's also just 1 over x. So I'll turn the 1 over x back on. Do they match up exactly? Not now. But they're kind of close, right? The blue and the green are still kind of close. They're just not perfectly matched. It looks like it needs an adjustment. Does anyone have an idea of what that adjustment might be? Okay. Do you remember, maybe you don't because we have these things, if I was going to take, say, log, and I'll do it, usually we don't put the base 10. There is a way I can do this with it's called the change of base formula. You might have learned this in algebra, that we could actually use the natural log to find this. And this will actually, if I only have the natural log, I can do this with the natural log of x divided by the natural log of 10. Natural log of 10 is what? It's a number, right? It's a decimal number, kind of not a very beautiful number, but it's a number. It's a constant. So I can think of this as being the natural log of x times 1 over the natural log of 10, which is a constant. Do I know how to take the derivative of natural log of x? Well, sort of. Well, we did just sort of learn, but we'll get there. It's 1 over x, right? And then we still have this sort of constant, right? Constant multiplier. So would it make sense that the derivative is going to be 1 over x times the natural log of 10? Ln of, and watch the magic that happens. As soon as I do that, the green and blue lines match up. Okay. And again, this is not, how do I know to do that? Well, I just figured it out after 20 years. This is the first time, you're the first class I've actually tried this with. I said, there's got to be a better way to teach this, right? We'll just prove it with a graph, graphically. I may have done it one time before, but so now they're matched up. So in general, the derivative of any log is going to be 1 over x, or whatever's in there, times the natural log of whatever the base is. And that doesn't, when we had natural log, what's the base of natural log? Natural log's base is e. And what's the natural log of e? It's 1. So in a sense, the derivative of natural log is really 1 over x natural log of e, but natural log of e is 1, so that's why we don't see it. It's a special case. So it's not really different, it's just special because that becomes 1. And we're going to see the same thing happens when we do exponentials. Okay? So if we just remember the general case, it's 1 over x times the natural log of the base, we got everything covered. Okay? And it's one of those things where it just is because it is. And even if you do a mathematical proof, there's kind of like this jump you have to do. It's not a direct proof. I've tried it before when I was a math major. In fact, I think that's what got me out of being a math major. No, I've stuck it out. But okay, so that makes sense. Then we'll work through them. While we're here, let's take a look at the other type of function. So I'm going to turn this off for now. Actually, I'm going to delete this one. We'll leave the derivative function here. I want to see what happens to exponentials. So let's look at e raised to the x power, because that's the other type of function we're going to do. So you see this function, e to the x. So that's what an exponential looks like. Whoops, what happened there? It's blue, so that's e to the x. That's its derivative. That's e to the x. That's its derivative. What's going on here? Could this function be its own derivative? Whoa, that's blows the mind, right? But it is. This is a function that its output is actually the rate of change of the function. This is like makes you almost believe that there's order to the universe, right? Because, and what do we call e? We call it the natural number because it naturally occurs. And when we use it in mathematics, it's got this special property that it's its own derivative. It's the only function in existence that is actually its own derivative. Kind of cool. Kind of, like I said, you think about it, you go, well, how can that happen? But notice how hard it's going to be. Which one, so if e to the x, its derivative is e to the x, which one is which? They both. So that's where you can kind of get, again, it's so simple because it is its own derivative. But then that's where the confusion comes. It's just like, did I take the derivative or did I not? Because it looks like I got the same thing. We're going to see that because we did the chain rule first, right? If we've got something more than just x up there, we're going to have to apply a chain rule, and that's where that comes in. So we're going to practice a little bit with that. These are both good functions for bringing in the chain rule, which we will do. But notice how they're pretty simple. Derivative of natural log, 1 over x. Derivative of any other log, 1 over x times natural log of x. E to the x, derivative is e to the x. Okay. Now what if we had a different base? Because I said e to the x is the only function that is its own derivative. Let me do this, see if I can. 10 raised to the x. Let me get rid of other x. Now, is 10 to the x its own derivative? No. But it's pretty close, right? Just like that natural log thing, right? Or the log base 10. What do you think is I like to call this a correcting factor. What do you think I need to multiply that by? And I'm not going to do it there because that's going to take the derivative. But it's close to being just its own derivative. Anyone have a guess at what might be the correcting factor? Thinking of, you've kind of already seen it tonight. Not 1 over x. What's the other part? So the base, natural log of 10. Right? Because that was a correcting factor. Remember, if we took the log base 10, it was 1 over x times natural log of 10, the base. So let's see if this works. If I multiply this by the natural log of 10, notice the now I've got purple and blue. If I take the purple off, it's blue. If I put the purple on, it's right on top of the blue. So the blue is the derivative. The purple is 10 to the x natural log of 10. Does it make sense that they're the same thing? They are graphing the same thing. So in math, we say if they have the same graph, they got to be the same function. That's the proof I'm using. And that's exactly it. This is, if I don't have e to the x, it's going to be its own derivative, but there's a correcting factor of the natural log of that base. Again, the special case is e to the x, because really when we take the derivative of e to the x, see, this is where it gets hard, it's really e to the x times the natural log of e. But what's the natural log of e? 1. So this is just 1, so this is just e to the x. So again, if you remember the general case, you'll also always get the special case. Okay, so there's always that natural log sort of correcting factor. Okay, and again, I got a couple slides and they summarize it and stuff, and we'll work through some examples together. But I just want you to see graphically it is, because it is. The graphs match up. It works. The proofs don't really help much. In my estimation, whether you're a math major, but certainly for a business major, we haven't covered limits to the level that would help us to understand that, so why even do it, right? Okay, any questions? Okay. Let's give a few examples now that we sort of already know what we need to know. Okay, so what's the derivative of natural log of x and log base b? So we know what they are. Here's log base b of x. This was their first slide or second slide or something, right? They came up and they just told it. And then we're going to say that's it. It is because it is. And we'll just sort of memorize that. And again, we don't have to go to the special case. We do on the next page. But if I was looking at natural log, right, of x, that's 1 over x, natural log of e, and natural log of e is 1, so that's just 1 over x. Okay, and again, in business applications, you'll probably be using the natural log the most, because those people in finance, and in finance you use e to the x and natural log to the x, so you use sort of in their pristine form. And so this is just showing, yeah, natural log of 3. Here's an example, 1 over x, natural log of 3. Now you can turn it into this. Usually we just like to leave it like this because natural log of 3 is not a very pretty number. Sorry about that. You know, it's just a judgment call there, I guess, but not real pretty. And it's because it keeps going on. It's not even exact, right? So it's better to use it in the form that we have it. Okay. And again, what we'll look at is where these things get a little tricky is because we'll look at them with their inside functions, not just x. It's like 2x squared and so that we've got a chain rule thing going on. But these are actually where the chain rule starts to make, I think, more sense because we've got an inside. Okay. Here's the special case. If it's natural log, then because that's a base e, it's just 1 over x. Okay, so we've already talked about that. And if I've got a constant multiplier, I still keep multiplying. So it's just kind of all the rules we've learned so far. The thing you just have to get in is we're not subtracting 1 from the exponent on this, because this has no, well, it has an exponent of 1, but this is not, with natural logs, with the logarithms, we're not subtracting 1 from the exponent, we're not bringing it down. It's a different case. Okay, it's just 1 over x. So that's the thing. Everything else we've been doing is something to some exponent, bring the exponent down, subtract 1. That's mostly what we've been doing. This is not. And be careful when we get to the exponential. It's also, even though it's got an exponent, e to the x, you do not subtract 1 from that exponent, although you'll get tempted to do it. Some of you will do it, but you'll catch yourselves. It's just, I did it a lot myself. Sometimes I still do it. So let's look at a few. So here's one. We got to use the chain rule, right? So what is the chain rule? We just learned it on Tuesday night. it's take the derivative of the outside function. What's the outside function? Natural log. So when we take that derivative is 1 over whatever's in there, right? X squared plus 1. And they kind of do this with a u substitution. They call it natural log of u, so it's 1 over u, and then they substitute back in. But what I'm just going to say is whatever's in that parentheses, it's 1 over it. Just write it. That's it. Well, that's the first step. Then, what was the chain rule? We have to multiply by the derivative of the inside stuff, the stuff inside the parentheses. Now, that one you might want to come over here and say, okay, what's the derivative of x squared plus 1? Okay, so I'll take that derivative, 2x plus 0. Oh, that's its derivative, so I need to multiply this by 2x. That is not in the denominator, it's just multiplied by 2x. So that's kind of the technique to get. And so usually when we write these as a final answer, we'll write this as 2x over x squared plus 1. Okay, that's its answer. That's the derivative. So 1 over the stuff on the inside, just put it there. The derivative generally will end up being in the numerator. Not always. There's a case where we're going to take a look at that it doesn't. And we're going to look at one where there's actually a double chain rule. So there's an inside to the inside. But that's it. That's it. Takes a little practice. The thing is, just getting you prepared after this test 2, we go back and we start going backwards. We're going to see this and we're going to have to think, oh, that's probably, it goes back to being a logarithm because this is 2x, so that's derivative in the top. So as you look at these, as you get them, try to connect that. Where did this come from? That came from a derivative of a logarithm. Because later on, when we go backwards, that's what will make it a little easier. We'll kind of start to see these patterns. When I take the derivative of this, I get that. So then when we go backwards, you'll start to see practice going back and forth. Okay. Don't worry too much about it. Again, it's down the road. But if you, at this time, just kind of say, where did these pieces come from? The top part came from the derivative of the inside. The bottom stuff was just the inside. Okay, so make that. Questions on that one? Let's see another one. What if we had log base 4 of x to the minus 5 plus 8? What's the outside part? Good. 1 over x to the minus 5 plus 8. That's just what it is. Oh, but while we're here, because we've got this, right, it's not natural log. This is still part of the outside derivative, natural log of 4. All right, because whenever the base is not natural log, we got to take that natural log of the base. Just kind of, I'll be honest, I typically forget about it. I have to come back later and say, oh yeah, there's that thing. Okay. Now, so that's the derivative of the outside. Derivative of the inside. What's the derivative of the inside? Negative 5x to the negative 6. Right, we subtract 1 from the exponent. Derivative of 8 is 0. And again, so you could put this up in the numerator, or since it's got a negative exponent, you could move it to the denominator and make it positive, but, you know, however you want to do it. But that's it, you know. Let's go ahead. I'm going to leave it in the top because I think it looks prettier that way. And I can see where everything came from. I can see that negative 5x to the negative 6, hey, that's the derivative of x to the negative 5. You know, so plus this 8 here, 8 was not in, and then natural log of 4. I would just leave it like that. Okay, so you see with these, we're going to get practice with that chain rule thing. Derivative of the outside, boom, plop it down, times derivative of the inside. this is a hard one. Can you see that this is going to be a double chain rule? Because we've got, inside the logarithm, we've got a square root function. Inside the square root function, but it's not too bad of one, because x plus 1, its derivative's just going to be 1. So we're going to be okay, but I'm going to take the steps to go through that this actually has 2 chain rules in it, right? So first of all, thinking of what we learned tonight, what's the derivative of the outside function? Natural log always has a derivative 1 over stuff. Okay, that's why I just said 1 over stuff. What's the stuff? It's all this stuff inside. So it's just, this is the easy part. And again, it's like we didn't really do anything. We just put it in the basement, right? But that's all we got to do. That's the outside stuff. Now we got to take times the derivative of the inside stuff. Well, what's the inside stuff? It's x plus 1 to the 0.5 power, right? That's a square root. So you see, that's going to be another chain rule because it's got an inside and an outside still. But the inside stuff's very simple. So what's the derivative of this one? Now this is where we do take this exponent, it comes down. So it's going to be 0.5 x plus 1. We subtract 1 from the exponent, right? So that's going to be a minus 0.5. But using the chain rule, what's the derivative of the inside? 1, right? Derivative of x is 1. Derivative of 1 is 0. So we multiply by 1, which is okay. We can make it disappear because when you multiply by 1, nothing happens. So it's not too bad. We could have skipped the chain rule. We still would have been right. But I want you to go through that process to say, actually got to take it, because had it been x squared, had it been square root of x squared plus 1, we would have had a 2x out there, right? So just remember that chain rule. Always look, if there's an inside part, take its derivative, multiply by that, and you'll never go wrong. So again, this is the derivative of the inside stuff, so we're going to have a 0.5 x plus 1 to the minus 0.5. Again, you could make that positive and put it down if you wanted to, because we've got 2 of them. Or you could, just do it like the 0.5 is technically the way we're doing this, because it's multiply. It's up in the numerator. This one, because it does sort of simplify, so if I take this negative 0.5 and I put it in the denominator, right, this is going to become, this is going to be positive 0.5, which is another square root of x plus 1. When you have a square root of something times the square root of that same something, what does that do? Cancels out the square root. Square root of 5 times the square root of 5 is just 5, right? So this one does simplify a bit. It becomes 0.5 over x plus 1. And 0.5 you could change to 1/2 if you, there's all sorts of algebra you can do, but again, I try not to do more algebra than we need to, because once we have the derivative, we could have stopped up here, we can get values. We can get rates of change, instantaneous rates of change. You doing okay? I don't want to confuse anybody, but it's just, again, natural log or log-based something is always 1 over the stuff. Natural log of the base, and again, if it's natural log, it's natural log of e times derivative of the inside stuff. That's it. And this is the summary. So natural log, and again, I put this maybe on a little card, and as you're doing things, just take a look at it. And that's how, I don't try to memorize stuff. I never did. I just see it, do it, and sort of pattern-wise, I would pick things up. It would start to make sense. Whenever I tried, I'd either memorize it wrong, or it wouldn't stick. That's because that's not how I learn. But you might be different, right, for just by you. So this is it. This is basically the same thing. It's just saying when you've got something more than x, you got some kind of a function, they put you also need to take the derivative of the inside, which is really what we do over here, but the derivative of the inside is just 1. So if you remember that, this is 1 over x times 1. That's the chain rule. You've always got it there. It's not that we're not using the chain rule. It's just that when we do use a chain rule, it's sort of redundant. Right? Over here, if u is something like 2x plus 4, it's not redundant. We get something new. And the same thing here. Basically, it's just the only thing. Remember, we got this sort of correcting factor. But if you think of it up here, we had the same thing. It was just a special case. It's natural log of e, which becomes 1 and disappears. So we could just, if we just remember this, all that's going on with this one, these are just when it's not the special case. Okay, so that's kind of our summary and how we doing. And again, we're going to have plenty of time because we've got a couple weeks where these are the last types of derivatives that we're going to do. So as we do everything else, we're going to be practicing again with these again and again. So it just takes some use. So that was pretty much all it had on logarithms. Okay. Now remember, there could be another function. We could also, because we've got the product rule, we could get a product rule involved here too. We could bring in a quotient rule. Okay. I looked over the homework. There's one of the homeworks that does have a product rule. So I'll leave that to you to kind of do if you want to see it. Maybe we'll see it a little bit later, but go from there. So this, from what we did in the exploration part, right? The derivative of any exponential, so the b is some kind of a number, it's not a variable, x is the variable. We're going to take the derivative of this, it's just its own self, b to the x, derivative is b to the x, times the natural log of the base. Okay. And so a quick example, 3 to the x, its derivative, so d dx is going to be 3 to the x times the natural log of 3. And then on the next slide you'll see it anyway, but I'll do it this way. E to the x, its derivative, d dx, is just going to be e to the x natural log of e, but natural log of e is equal to 1, so we just write e to the x. Okay, so that's, we make a special case of it, but again, I always got one more thing to remember. If you just say it's not really a special case, it's just that it becomes 1. To me, that when I started doing that, it simplified it for me. Okay. So they talk about this, yeah. What's its derivative? E to the x. Okay. But for a quick example, let's go with, what if we had e to the x is 3x squared minus 4x? What happens when we want to take this derivative? No. Take the derivative of the outside function first, right? Chain rule. What is the outside function? E to the x. This is our outside function. What is the derivative of e to the x? It is e to, so you just copy. So that's the nice thing. The first thing you do is just copy carefully. It didn't change. And that's why it says it's easy, but it's like, that doesn't feel right. But it is. So that's the outside derivative. It's its own derivative, even if I get that funky stuff in there. But now what do I do with that exponent? That's an inside stuff, right? So I'm going to multiply by the derivative, and I'll do it up here, 3x squared minus 4x, so 2 times 3 is 6. Let's kind of walk through the paces here. So I bring the 2 down, subtract 1, so x to the first power. This is 1, so 1 times negative 4 is still negative 4. Subtract 1, you get x to the 0, which is 1. So the derivative is 6x minus 4. That's what I multiply by. That's its derivative. And again, I don't want to multiply, I don't want to distribute it out, because as I do this, I start to see, oh, this looks like it's the derivative of that. And that's the patterns I want to be able to see. And I say, okay, I used the chain rule. Yes, I could do some algebra and, maybe things simplify or something, but if we can see the patterns, here's the derivative and here's the derivative of the inside stuff, we're just multiplying them, we got it. Okay. So that's what we use e to the x for a lot, because function inside. Now they give us, so I gave you a harder one than they're giving us here, right? So what's the first step of taking the derivative of e to the x? Just copy it over, right? Just copy it. And then we're going to multiply it by the derivative of that inside stuff. And that exponent is really, it's a grouping symbol. If you want, I like to kind of put a parentheses around it to emphasize that's where the inside stuff is. Derivative of x squared is 2x, derivative of 1 is 0, so that's it. And again, what you'll see is a lot of times they'll put this first, and so that might be why when you see the answers, it looks like they took the derivative of the exponent first, right? Because I'll write it like this, 2x e to the x squared plus 1. But again, my suggestion is always take the derivative of the outside part first, because that's really the easiest part, especially with e to the x. You just copy it. Had this been 5x squared plus 1, how would it have been a little different? Would have been this times what? Natural log of 5. Because that's the correcting factor. Then times the derivative of the inside stuff, which is just 2x. And again, when they finish writing this out, they would probably write it as 2x natural log of 5, 5x squared plus 1. And they might have some parentheses, they might not, but you can see it looks like what order they do it in. I would do it this way. It's copied down. Since it's not e, since my base is not e, I have the natural log of the base. That's always there. And then derivative of the inside stuff. Okay, chain. And now, what's the difference between a function and its derivative? What does the function give us? So let's say a profit function. Profit function gives us what? Don't think too hard. Gives you the profit. Gives you the amount of profit. The derivative of the profit function gives you what? Marginal profit, which is profit on the next piece. It's the rate of change of the profit. Okay, so that's the way to think of it. The original function gives you some kind of a value, profit, cost, revenue, whatever. It gives you that value. The derivative always gives you a marginal, or what in terms is what would the next one cost. So it's the change. What is it, what's the change going to be? What's the rate? Okay, good. That's the key. That's if you come out of here with nothing else out of this course but just that, you might not pass, but you'll have the key part of the content. You'll be fine. You'll be able to do all this. You want a little bit more than that, but you definitely need that. I got people that are good at taking the derivative, but again, and I was one of those, I could do the derivatives, but when you asked me really what they were, it was just I was so busy doing it, I couldn't describe them real well. But I've worked with people, my boss, he was not a math major. In fact, he sold used cars. He was a used car salesman, but then he started selling insurance. He's a great salesperson because he connected with people, and he was sharp with his numbers. He could look at data and stuff, and he could tell you the rates of change. He could do this, and I had all this calculus. I'd be like 2 hours behind him. I said, oh yeah, you're right again. So, but he could look at stuff, and he would know. So he was applying that concept in there. So again, here's a big formula sheet of what's all going on, but again, if we follow this first thing, e to the x is its own derivative, but remember, it's really times the natural log of e, which is 1. So that's the same rule of here, so we don't really need this. This is just sort of a special case. And if we think that it's when I take the derivative, there's always the chain rule, but the chain rule of x, when I take the derivative of x, it's times 1, then I don't really need all this stuff. Just remember that there's always a chain rule that we're going to do. And it's kind of just, so then it's like, oh, it's just one, this is, or I guess if you remember this one, it has all these special cases built in. So you don't have to memorize 4 different things. It's just, okay, exponential, the base, it's a copy of itself, natural log of the base, always even with that one, and then the derivative of the exponent. And oftentimes, if it's just x, the derivative of the exponent is just 1, so it's just simpler case. But if you remember just this one, you've got it all. I think we've got one more application we're going to take a look at. And this actually comes from the homework, and I thought, I think you'll be fine with it, but it assumes that you remember the formula for continuous compounding. How many of you remember the formula for continuous compounding? How many of you, I don't even know if they still have this shampoo. It was big in the 70s and early 80s when I was growing up. Pert? Anybody heard of Pert? It's a shampoo. That's how I remember it. It's also, this is your principal, e to the RT, your rate times time. So that's, but again, and I even used Pert shampoo because it was cheap. So that's how I remember it. So that's what you need to remember to be able to do this. And then they tell you, okay, what's the principal? 20,000, we're going to invest it. What's the rate? 3.5, so we can fill that in. But without knowing this formula, you're just kind of, you don't know where to start. So this is really a function. Accumulated value of t is p, which is 20,000. E is the natural number. R is the interest rate, so 3.5 as a decimal, excuse me, is going to be 0.035. So just be careful if you do it 0.35, that's 35%, so make sure you get your decimals right, times t. So that's up, so this is our inner function, right? And what they want is how fast is the balance growing? How fast is it growing? What's that? That's a rate. If they want a rate, what do we need to give them? A derivative, right? So that's they don't say take the derivative, but they want a rate of change, how fast. So that says, okay, take the derivative, and they want it at 2 years, and then we'll plug in 2. Okay. So what's this derivative? The 20,000 is just a constant multiplier, right? So it just tags along. We still got our 20,000. E to the some power is itself, is its own derivative, so I copy that. 0.035 t. And then I multiply by the derivative of the inside. What's the derivative of the inside? I'll do it up here just to kind of emphasize t to the 1 power. Remember, the 1 comes down, so it's 1 times 0.035, and then subtract 1, t to the 0, which is 1. So it's just going to be 0.035. Okay, so what we see, and what's kind of cool, when I did this earlier, I go, wow, I've been teaching math for 20 years, I didn't really realize this. Notice, when we're doing continuous compounding, this is the interest rate times that. So that's how much interest is just, if it was an annual basis. This is getting us the compounding, right? The exponential. And you'll see you actually, if this was your account, you're actually at the end, you're getting more than 3.5% simple interest. You're getting compounded interest continuously, you get more. But anyway, it was kind of cool when you take that derivative. There's our rate, isn't it? So it's like this part, because what are we going to do? We're going to take 20,000 times 0.35, and so that's 1 year of interest, right? What's that? That's I think it was 700. See, 20,000 times 0.035, 700, yeah. Times e to the 0.035, and since we're going to plug 2 in for t, right? This is because they actually want the value. So derivative, and so this is just a simple interest. This gives us the interest with the compounding. Okay, and it's giving us the change, how fast it's changing at year 2. And you'll see if you do this with year 10, because it would be the same derivative, right? It's the same derivative that we could plug in year 10. We see we get more interest in year 10. So this is actually, what this is going to give us is the interest we earn in year 2, without actually ever calculating what the accumulated value is in year 2. Right? We could do that, but what we end up with is when we do this, we get like what, 750 something. Has anyone got a calculator that can? So this is 700 e to the here, I got an e to the x. Oops, I need to put that in. So 0.35 times 2 e to that power times 700. 750, 76, if you round it. So this is 750.76 rounded to the nearest cent. Okay, that's the amount of interest that would be earned in the second year. First year you would have earned a little bit less because, right, compounding, you get it added on and the principal grows. So remember, when we're using the derivative function, we're getting the rate. So that's the amount of new interest in year 2. If I plug in up here, if I put a of 2, what am I going to get? I'm going to get the balance at the end of year 2. That's going to be 21,000, maybe 22,000 something, 21,400 and something. Just get, because it's 2 years of interest, right? So, and you got compounding interest. But this gives me a balance. This gives me how the balance is changing year to year. So it's kind of cool. I can use that derivative, and I can say, well, in 10 years, well, what's that rate of change? What's that going to be? Okay. But it's just kind of cool. I mean, as you go through these, you start to see from the derivative, I'm getting the annual interest, and then this is giving me the compounding. So it's kind of cool. And that's, there's no more slides. So when I push on the button and it doesn't go anywhere, I mean, that's the end of the lecture. So, and if you go through the homework, it doesn't get too, it doesn't get too funky, any more funky than it. Mostly, there's just that one that there is a product rule, so I'll let you, but it's kind of clear. There's a big parentheses, and then there's a natural log of something with a parentheses, so you just say, oh, that's last, so I gotta do a product rule as well as a chain rule, okay? And kind of play with that. It may cause a little struggle, but don't worry too much about it. If you got a question about it, we'll take a look at it first thing Tuesday. But everything else is just like we were doing. Just follow that chain rule. They're simple derivatives, right? Natural log is going to be 1 over the stuff. E to the x is going to be a copy of the stuff. It's just its own derivative. And then we've got that correcting factor of natural log of the base if it's not the natural number. And then we just have to remember, whatever's inside, we also have to take its derivative because of the chain rule. That's it. We don't get too much complicated. And we're going to get more time to practice them. And this is sort of, again, the last of the new derivative techniques. While implicit derivatives is something a little different, it's new, but it's the way we go about it is just that we're going to do it with two variables. It's like we're doing the same thing, We've been doing it with one ball in the air. Now we're going to put two balls and do derivatives of two things at the same time. And it's just a little technique that we use to keep track of which one we're working with. But it's going to be okay. And then it allows us, the rest is our applications. We start to apply it, which is really cool. All right, and we got spring break in there somewhere, so if, get ahead and then go travel into the Amazon or something, wherever you want to go. I'd like to go there someday. I'd like to actually get lost in the Amazon. Never come out. I don't know.
If you get lost, you're not coming out.
Yeah, if you get lost, you probably never come out. Anyway, that's it. Have a great weekend. If you have any questions, stick around and we'll get it all